A subspace H of a vector space V is a subset of V so that 1. The zero vector is in H, 2. For u and v in H, u plus v is in H, and 3. For u in H and any scalar c, c times u is in H. And this should look slightly familiar. It's literally the same definition as before. You're going to see a theme in this video. First, R2 is still not a subspace of R3, because R2 is not a subset of R3. Here's another example. P2 is a subspace of Pn if n is bigger than or equal to 2. And let's prove this. Before we start, we need to show P2 is a subset of Pn. Any element of P2 is a polynomial with degree less than or equal to 2, which means the degree is less than or equal to n, so it's an element of Pn. So cool. Now we need to show the three properties of subspace. First, the zero polynomial is in P2. Second, take two vectors in P2, or quadratic polynomials, and add them together. The result is in P2. Finally, for any scalar c, c times a quadratic is still a quadratic. Therefore, P2 is a subspace of Pn. Let's follow this up with a couple of definitions. Let V be a vector space. The vectors v1, v2 up to vk are linearly independent if c1, v1 plus ck, vk is equal to 0. Only has c1 equals c2 equals ck equals 0 as a solution. Again, this should be familiar. As an example in P2, the vectors 1, x, and x squared are linearly independent. X is not a real number, it's a variable. That means it's not a scalar. A basis of a vector space V is a subset of V that is linearly independent and spans V. The dimension of a vector space V, denoted dim V, is the size of any basis of V. The set 1x, x squared is a basis of P2. Think about it. All quadratic polynomials are linear combinations of these vectors. That means the dimension of P2 is 3. The set 1x, x squared, and so on is a basis of R adjoint x, which is the set of all polynomials with real coefficients. That means the dimension of Rx is infinity, which is quite interesting. Many theorems and definitions transfer directly from Rn, and they're in the notes. In particular, the basis theorem. But note, the basis theorem only holds for finite dimensional vector spaces, and this is kind of a big deal.